Far out in the Milky Way, a tiny particle of matter flies like a bullet through the vacuum of space. Propelled by colossal forces, the particle moves at nearly the speed of light, zipping by stars and the glowing clouds of gas where stars are born. Suddenly, a planet looms directly in front. Unstoppable, the high-energy particle rips into the planet's atmosphere. It collides with a nitrogen atom, destroying both the particle and the atom in a flash of pure energy. Now that energy creates new particles, which cascade downward, causing more collisions as they go. Soon, thousands, then millions of more particles spread out in a widening cone and then slam into the planet's surface. Earth has just been hit by a cosmic ray.
During the past century, astronomers have come up with a multitude of ways to get information from the universe. Stars give off visible light, but they also give off infrared, ultraviolet, X-rays, and other forms of light our eyes can't see. What makes cosmic rays so interesting is that they're not another form of light. They're bits of matter that are coming directly to us from deep space.
Cosmic rays carry information about powerful forces and events taking place thousands or even millions of light years away. But to understand what cosmic rays can tell us about the universe, we need to know how they are produced. In fact, it took a while for scientists to understand that cosmic rays even exist. The idea has its roots in the discovery of radioactivity by the French physicist Henri Becquerel in 1896. Radioactivity is the particle radiation that comes from atoms breaking apart spontaneously in the environment. When it was discovered, scientists realized that radioactivity might explain why they could never get an object to hold on to its static electric charge indefinitely. Because of radioactivity, in rocks and soil, there are always particles present near Earth's surface. Those particles can interact with anything that has an electric charge, causing that charge to gradually leak away. Over a century ago, scientists predicted this effect would disappear if they could take an electrically charged object away from Earth's natural radioactivity at the surface. The only question was how. The answer would come in 1911, when Victor Hess, a physicist from Austria, began a series of daring balloon flights that would eventually carry him and his instruments to a height of over 5 kilometers, roughly half the cruising altitude of a commercial jet airliner. As he ascended, Hess measured the presence of charged particle radiation like the kind produced by radioactive materials. At first, the radiation diminished with height, exactly as expected. But then there was a surprise. Starting around 1,500 meters, the situation reversed. Hess found there was more radiation than at sea level, and it was growing with altitude. By the time Hess landed, there was no longer any doubt. Earth was bathed in radiation coming from above, and a new field of science was born. Scientists eventually started calling the mysterious space radiation cosmic rays. By the 1930s, the invention of the Geiger counter had made it clear that cosmic rays were pummeling Earth at an astonishing rate, amounting to tens of thousands of incoming particles per square meter every second. Most of the particles were relatively low in energy, but some had enough energy to pass through rock, or even up to a meter of lead. Then, in 1938, the French physicist Pierre Auger took some Geiger counters high up into the Alps to measure cosmic rays there. He found that when two Geiger counters were set far apart, they sometimes recorded cosmic rays arriving at exactly the same time. Auger had discovered cosmic ray showers, bursts of particles that rain down in a widening spray, following the destruction of a single, much more energetic particle higher up in the atmosphere. Based on the size of those showers, some of the cosmic rays coming in from deep space were clearly more energetic than any particle produced on Earth. Now, scientists found themselves embarking on a new quest to understand where in the universe those energetic particles were coming from. Thousands of light years from Earth, a massive star ends its life in a brilliant explosion. This is a supernova, a stellar cataclysm that is one of the most energetic phenomena in nature. As the powerful shockwave expands, it creates a wreath of glowing gas, like this one, called Cassiopeia A, here revealed in striking detail by the Hubble Space Telescope. But could such an event also give rise to cosmic rays?
The riddle of cosmic rays is one that's being solved in stages. The ultimate goal remains understanding how these high-energy particles from beyond our solar system are created. But to get there, scientists first had to figure out what kind of particles they were.
For the most part, those particles never reach us here on the ground. Instead, they strike the atmosphere and unleash a torrent of secondary particles that shower down like so much subatomic shrapnel. By studying these secondary particles in the 1930s and 40s, scientists gradually narrowed in on the true nature of cosmic rays. What they found is that most cosmic rays, about 90% of them, must be single protons. Protons are positively charged particles that are part of every atom in the universe, but most of them occur in the form of hydrogen atoms. Atoms that are made of a single proton orbited by a single electron. Hydrogen is the most abundant element in nature. Stars are mostly composed of hydrogen, and so are the vast clouds of gas out of which new stars form. So whatever is making cosmic rays and sending them our way, it has plenty of raw material to work with. In 1947, a high-altitude balloon experiment revealed that most of the remaining 10% of cosmic rays are made of the nuclei of heavy atoms, like iron. Like protons, these atomic nuclei are stripped of their electrons, and they've been sent rocketing through space by a powerful force. But what? Even solar flares, the giant explosions that erupt from the surface of the sun, cannot account for the energies behind these heavier cosmic rays. But solar flares do offer us a hint about how cosmic rays are created. Because solar flares are caused by the release of magnetic energy. Under the right circumstances, a magnetic field can be used to accelerate an electrically charged particle, like a proton, to enormous speeds. Today, this principle is at work in the Large Hadron Collider, the world's largest particle accelerator. where huge superconducting magnets are used to send protons careening around a giant ring 27 kilometers in circumference. When the protons collide, the energy release is enormous, generating new particles that allow scientists to explore the fundamental properties of matter. Amazingly, some of the highest energy cosmic rays are millions of times more energetic than the protons in the Large Hadron Collider. It means that somewhere out there in space, nature has created its own particle accelerators that would dwarf anything humans have built on Earth. But identifying them has proved a major challenge. Starting in the 1980s, an experiment called Fly's Eye in the remote Utah desert used sensitive detectors to spot the faint ultraviolet glow of cosmic ray air showers high up in the atmosphere. This allowed researchers to see what direction any particular cosmic ray was coming from in the sky. Yet, this did not help scientists figure out where cosmic rays ultimately come from. The reason is that the space between the stars is a complex network of magnetic fields that thread their way around our galaxy. And these fields have been bent and twisted by the turbulent motions of ionized interstellar gas. The magnetic fields completely scramble the directions of cosmic rays moving through the galaxy, so that from Earth's point of view, they appear to be coming from all over the sky, leaving no hint about where they originally came from. In their efforts to explain cosmic rays, scientists had run into a significant roadblock, one that would require them to search the heavens in a new and different way. This is our Milky Way Galaxy, home to hundreds of billions of stars and vast clouds of dust and gas that stretch on for thousands of light years. It is a huge and complex system. And hidden somewhere within its depths are the sources of high-energy particles we call cosmic rays. As early as 1949, the nuclear physicist Enrico Fermi proposed the idea that cosmic rays are produced when protons and other charged particles are accelerated to high speeds by bouncing around within a changing magnetic field. But where in the galaxy might conditions make such bouncing around possible? Because cosmic ray particles are intensely energetic, the sources that create them must be able to somehow provide that energy. And those sources may also give themselves away by throwing off a high-energy form of light called X-rays. Here on Earth, X-rays from space are absorbed by our atmosphere, so X-ray telescopes must do their work orbiting high above Earth's surface. Today, the Chandra X-ray Observatory is our most discerning X-ray eye on the sky. Chandra has been used to peer into some of the hottest and most energetic regions of the galaxy, revealing views like this of the Carina Nebula, where interstellar gas is cooked to millions of degrees by newborn giant stars. This is a high-energy environment, but not one that has the kind of magnetic fields needed to accelerate cosmic ray particles. So instead of looking at places where stars are born, cosmic ray hunters have zeroed in on those places where giant stars have died violently. This spectacular ring is the remnant of a supernova, a vast stellar explosion that sprays matter outward in all directions, creating a rapidly expanding shockwave. The leading edge of this bubble can move at tens of thousands of kilometers per second, but that's still nowhere near the speed of a cosmic ray particle. However, scientists after Fermi realized that supernova shockwaves can compress and strengthen magnetic fields in the surrounding gas. Then, charged particles moving back and forth across the shockwave can pick up more and more energy through a process called Fermi acceleration. Eventually, the particles would be moving fast enough to break away from the shockwave and fly off into the galaxy. Here at last was a theory that could explain cosmic rays, but proving it would require another kind of space observatory. Fittingly, that observatory is NASA's Fermi Space Telescope. Named after Enrico Fermi, it has special detectors that can pick up gamma rays, a form of light even more energetic than X-rays.
5, 4, 3, engine
Launched
start.
in 2008, the Fermi telescope had been used to study the most extreme phenomena in the universe,
A gamma-ray telescope searching for unseen physics in stars.
like the supermassive black holes that lie at the centers of distant galaxies, or mysterious explosions known as gamma-ray bursts. And Fermi has also turned its attention to two of the most interesting supernova remnants in the Milky Way. One is W44, a dramatic shell of expanding gas located 10,000 light-years away in the constellation Aquila the Eagle. The other is IC443, nicknamed the Jellyfish Nebula. It lies roughly 5,000 light-years away in the constellation Gemini. What these two colorful bubbles have in common is that they are both the result of supernova explosions expanding into dense clouds of interstellar gas. In theory, this should be the perfect situation for generating cosmic rays by Fermi acceleration. The Fermi spacecraft is the perfect tool for testing this idea. Its sensitive detectors can distinguish between gamma rays that are produced by different kinds of physical processes. But it would take more than 4 years of gathering data with Fermi for scientists to be sure. Finally, in February 2013, they were ready to reveal their results. What they had found was a clear signal, the first ever seen, of protons at high energies occasionally colliding to produce gamma rays. The type of signal exactly matched what was expected if the protons were being accelerated on their way to becoming cosmic rays. 100 years after cosmic rays were first discovered, the Fermi telescope had finally captured a glimpse of cosmic ray creation.
Scientists now know more about cosmic rays than ever before, but the search doesn't end here. Although they are rare, the highest energy cosmic rays are so powerful, even a supernova shockwave isn't enough to drive them. So now the search for new sources of cosmic rays is reaching beyond the boundaries of the Milky Way.
This is M87, a giant galaxy about 60 million light-years from our own. Deep in its core lies a black hole so huge its mass is equivalent to more than 6 billion suns. As it devours gas from the surrounding environment, the rapid spin of the black hole causes some of the gas to escape, forming a jet that extends hundreds of thousands of light years into intergalactic space. The jet is wrapped in magnetic fields that may just be strong enough to create what are known as ultra-high energy cosmic rays. Because they are so rare, the experiments that hunt for these particles are huge, covering thousands of square kilometers in an effort to capture just a handful of the most energetic particles in nature. But if the theory proves correct, for the first time, these experiments may be able to prove that we are being hit by matter from another galaxy. Thanks to the discovery of cosmic rays, we know we have a direct connection to some of the most powerful phenomena in the universe. Now, as a new chapter of exploration opens before us, we are learning just how astonishing that link to the cosmos may prove to be.